spell out the elements
Yeah.
of this model? Because, for example,
Yeah.
if you were running, thinking a linear regression or whatever, you have the variables,
Yep.
clearly spelled out, the positions, etc., etc. And here we're visually seeing
Right.
how this works,
Yep.
but it would be helpful to see how it compares to some models that we made.
Sure. Okay. So this is great, and I'm grateful for all the questions and feedback. I'd like to. We're going to be engaged in a triage process here, where I'm going to make some comments drawn from the slide decks which I've provided to you on the site and so on, of things that I think will be most helpful for trying to address some of the questions that are coming up, and I will change the ordering of some of my plans because of it. So let me see if I can give you a glimpse of what these models are in a more structured way, in a way that's less buzzing and blooming, right? So let's go. I think on the basis of this to this dynamic modeling type. And actually, I'm going to, even before this, there's a feature here within this first presentation, which talks about system science as a whole. Okay. So I've talked about these simulation models for representing hypothesized causal relationships involving how diverse factors relate to each other. And I've said, they provide a way of examining system-wide consequences of changes in one or more areas of the system in light of these hypotheses. They don't make our hypotheses right, but they help us more quickly identify inconsistencies between our hypotheses and what we see in the world, and understand if we posit this structure of how things might work, what is the logical implication for how, say, a tobacco tax might affect, elevated tobacco tax might affect the initiation in, the 10 to 14-year-old range or what have you. So these models are designed to help us and other system actors to understand vulnerabilities, leverage points, where we can change things most effectively, where we might be especially vulnerable to uncertainties or to exogenous factors that we can't control, like the state of the economy, ways that we might fruitfully change how the system works. Maybe it's, up at Saskatchewan, we're going through a serious rethinking, informed by modeling in a central way, of how care is delivered between hospitals and between long-term care facilities and other home care options, and options associated with community options for individuals, and this issue of changing system structure. What placement of a new resource would make the biggest gain? Models can be used for that, and ways that people from different areas of the model can work together. So what are these models? They go by various names, and this is one of the most confusing things about system science. Some people call it system science. Some people call it complex systems or complexity science. Some people call it mathematical modeling. Other people call it causal modeling, but it's a separate sort of causal modeling than we talk about in the Judea-Pearl sort of path analysis tradition in biostatistics. The defining goal here is, examining dynamic behavior resulting from hypothesized causal structures. And what distinguishes these models is that they depict, they have a mechanistic depiction of processes in the world in a way that your typical statistical model will not. Now, I should mention here, I am a big practitioner these days of computational stats. I've worked very closely and contributed to biostatistical models with competing risks analysis and survival analysis. And I believe that those sort of statistical approaches are incredibly important and complement these models. But those statistical approaches, whether more traditional ones like I've just mentioned, or whether we're dealing with more recent computational statistical models with different latent variables, such as through Bayesian graphical modeling, they are not mechanistic models of processes in the world. And that's really what distinguishes dynamic models. They depict at a certain level of abstraction posited structure of how things work. You know, the plumbing of what leads to what leads to what. The kind of physics of the system as we talk about it. What pushes on what impacts what. And here, the system is depicted as being in a certain state, and there's a description given about how it evolves, that state evolves. So it simulates the step-by-step evolution of the state over time. And this holds for any number of different types of particular models. Agent-based, discrete event models, system dynamics models, microsimulation models, they all fall into this basic rubric. We're depicting the state of the system at a given time and rules for how it evolves over time. In system dynamics, are specified differential equations. And in agent-based models, are specified things with state charts, et cetera, like we've seen. But they depict how the system evolves over time in terms of the mechanics of it. What's going on in terms of the processes in the world that happen to give rise to data that we observe. So they're positing sort of processes out there in the world that are operating and over time to give rise to observables. And as such, they involve a lot more latent state than your average, even Bayesian graphical model. They involve positing sort of many types of latent state in the system that may not be readily observable, or you may not have direct data on large pieces of it. And this is key. Why do we do this? It's not just for fun. It's not just because it's interesting and pretty and neat. It's because by depicting causal structure, they allow us to ask about counterfactuals. They allow us to posit, if we were to do this, even though we've never done it, if we were to combine this intervention with that one, if we were to put in place this new way in which care is delivered in long-term care facilities, how would it impact things in terms of the burden of illness in the population, in terms of costs, in terms of quality of life measures, et cetera. So they allow us to examine counterfactuals given these hypotheses. And, you know, the fact is that we see this all over the world in terms of other areas. You would never trust yourself to fly in a plane to Sydney, Australia, if the pilot had not undergone extensive training in thunderstorms and flight simulators, right, before flying a plane. You want that pilot to be very versed in how a plane responds in various adverse weather conditions, counterfactual conditions, so that you can put confidence in them they'll be able to handle that thunderstorm brewing off the coast of England right now. You know, in the whole climate policy areas, models, of course, have been central and by some individuals contentious, but have been central to policy discourse. You know, whether it's power plant area driver training, street design, I mean, people have been using these for years, for decades. And really, public health has been a little bit out of the loop in terms of this because they're central to engineering decisions, central to decision-making in budgetary areas, and now they're coming to the fore within the public health process. So what's going on here? Well, at some levels, you know, we have often a mental model of how things work in the world, but it's inchoate, it's not completely expressed, a lot of it is tacit, a lot of it is trapped in our head, and it's hard to share. But that mental model is incomplete, and we critically, as individuals, tend to be quite good in understanding the implications, adding all the pieces up and comparing them to evidence externally. We're just very poor at sort of putting them all together. And as a result, it may be disconnected from what's actually going on in the world in many certain respects. Models provide us this way of sort of taking that out of our head, putting it into an explicit form that helps us, using simulation, observe the dynamic implications, the behavior over time that results from a model like that, compare it to what we've observed from the world, and sometimes collect data, prioritize our data collection as a result. We need this piece of data. We need to go check, does the model result match this data? Or in some cases, putting into place an intervention and seeing the results, comparing it to what the model would have anticipated. And really, this is kind of the broader enterprise in which modeling is embedded. It's not an enterprise of going and creating crystal balls in isolation. It's an enterprise of learning more quickly from evidence about the world. You know, my colleagues in Hopkins, Josh Dean, or at Pitt, Don Burke, head of the School of Public Health there, they've created lists of dozens of ways the roles models play. Yeah.
Do you need a break? For 3 o'clock. Yeah.
Okay. There'll be a good break coming up. Yeah. So listed dozens of ways models have been used. You know, broadly speaking, these models are characterized by this evolving state. They specify incremental change, system behavior is emergent. What results from the model? In contrast to statistical models, and this is related to, remind me your name? Daniel. To Daniel's question. In contrast to statistical models where you take a logistic regression or take a model of change over time that assumes some functional form, we're assuming a certain form in the model and perhaps regressing against coefficients to arrive at estimates for coefficients for the betas. Within a dynamic model, the model's behavior over time is emergent. In other words, it's not pre-programmed in. It results from the interaction of a variety of processes captured by the model, presupposing certain behavior, and instead, sometimes we get surprising behavior that mimics emergent behavior we observe from the world, or that's otherwise unexpected, and it may be behavior we can sometimes learn from. Typically here, the model behavior cannot be pre-specified in closed form. Derive ahead of time what the behavior of this model will be without running it. Generally, these models exhibit this process of nonlinearity. We talk about the whole greater than the sum of the parts. The responses to multiple interventions is very different than the sum of the responses to each intervention in isolation. Doubling the impact of a policy on some piece of the system does not merely double the response of the system. It's path dependent. You have tipping points where the system can go from one phase of a infection that was essentially almost extinct in the population, suddenly becoming endemic. Think about measles in the context of failing vaccination rates. You had achieved herd immunity, and now you're crossing a point, and now it's circulating on a yearly basis, and where heterogeneity can have a big effect. The analogy I'd like to use here, folks, and this is another very important analogy, is models are like maps. Models are like maps. All maps are limited. They're useful because they're limited. If we have a map of the Boston area, we want to get from here to Long Wharf, we use one type of map. If we want to figure out why flooding is occurring, in the area of Boston Hill, we'll use a different map. Models are useful because they omit details, and they represent abstractions. They hide certain details and bring out effective details. Models, like maps, are specific to purpose, and what things the model will include will depend on how it's to be used. George Fox once said about statistical models, but it's a more general comment about modeling. All models are wrong, some models are useful. So it is with maps, right? We don't expect a map to have every blade of grass on our front lawn, but it's still useful for purpose. Now, if I give you a map of Boston's electrical grid for you to figure out how to drive across Boston, you'll say, well, that's not the right map for the job, and that's exactly right. And so it is with these sort of models. Models are like maps. They hide detail. They can be useful for certain purposes, but they have spheres of natural application. And with these models, we need to always keep in mind, what is the appropriate use of this model. I want to distinguish between three things in the model: endogenous factors that are calculated by the model, produced by it, generated by it, is what Josh Epstein calls it. Exogenous factors, factors that are represented in the model but are presupposed or pre-specified, versus those that are simply ignored by the model. And this is a broad characterization which again holds for all types of modeling. Okay, so a couple key take-home messages thus far, and then after the break we'll talk about some particular features of types of models. So first of all, addressing many larger health problems is especially hard because they exhibit features of complex systems. I have a whole slack of slides that realistically I don't have time to give here, given a lot of the great discussion, and it's going to inform this too much for me to go into it. Oh, thanks. But fundamentally, it's many health challenges that exhibit these features of complex systems. You think about something like the impact of obesity on chronic disease, ostensibly a biomedical issue, as people conceived of it a couple decades ago, and you suddenly find there's all these levels, these layers of issues, biopsychosocial factors, not just biomedical ones, factors having to do with the context and the ways in which people's norms evolve, involving weight and involving diet and involving physical activity. So many larger health challenges, whether it's challenges of tobacco or obesity or antibiotic resistance, etc., these exhibit features of complex systems. To solve them are going to require grappling with human behavior and its interaction with biomedical issues in a way that transcends our ability to address with traditional reductionist techniques. We've been very good in our scientific enterprise in recent years. I'll be with you just a sec. In terms of taking things apart and understanding how the pieces work. And system science, ladies and gentlemen, is about taking those pieces, hard-won understanding, and putting them together. And both are needed. This is not about we can't do reductionist science anymore. No, it's really useful to understand how aspects of the insulin regulatory apparatus works. We need to understand that in context. We need to put the pieces together to understand what's really best for an individual. And that putting pieces together, that is the enterprise of complexity science and system science. Yeah.
What you're describing is like a much more accurate depiction of reality. I'm wondering if there's any example where an issue is not complex.
It's a good question. There are certain issues where traditional reductionist attempts understanding tends to work very well. You go to an orthopod, and they'll give you lots of examples. You break your arm, you want me to be thinking about your social context and so on? No, I'll come and set your arm for you, okay, buddy? And maybe I'm exaggerating a bit, but there are certain things that are more biomedically straightforward and where the linkages to the context are not as big. But I'll tell you that you're right in the sense that a lot of issues that are traditionally force-fit into a purely biomedical model, I think will be re-examined eventually. You consider cases, I know someone who didn't go to the doctor to actually address a broken arm or leg, I can't remember which it was, because of trust issues. There was an issue, he didn't feel that he'd be able to go there and develop confidence that they'd be able to set it well. So we end up, seeking care elsewhere. The point is that even in something as simple or straightforward as that, there are issues having to do with that transcend biomedical. I would say that traditional statistics, biostats, is very effective for certain types of understanding, teasing out the associations between certain factors and outcomes. In cases where the feedbacks are not as pronounced, where there's not a coupling between factors over networks, where the pathways are more clearly mapped out already, and where they're more localized. So I guess I would say I do believe there are some areas where purely traditional techniques, unaided by complex systems approaches, can be very useful. but I think complex systems do appear, they raise their head in a lot of different areas.
That raises a question actually. So at one level, we do this basic causal mechanism for hypotheses using a finite number of ways, like two variables at a time, but you're like engineers, manipulate the thing at 90 degrees, 60 degrees, and see how the wave flows in a tunnel. And there is some value to that. On the other hand, you are correct. So the reality is much more complex, and sometimes, we need to take the complexity and the understanding to really understand where we are going with this trajectory. In the past, I don't think we had the capacity to do that kind of a computation, and now we have it, right?
That's right.
We develop a complex model, but we never had the capacity. Now we have the capacity, mathematical and computationally, to do this model, and maybe that's what we should be doing.
Yeah.
However, if you go, I don't know whether you have the slide or not. I don't know how many of you have seen this slide from United Kingdom on obesity.
Yes, I have.
It's like a spaghetti in a bowl.
Indeed. Indeed.
So at some point, I want to know, where do we draw the line? Instead of simple model with two variables, or this,
No, it's actually, I think you're talking about, I cut it out. It's related to Sandro's, sorry, this is it. This is it.
That's the one.
Yeah.
This model that come out of some sort of United Kingdom.
Right.
I can't even begin to handle it. If I want to if I want to intervene, I don't know. I mean, I will give up right away.
Right.
So, in building on the question, where do I draw the line between my simple 2-3 variable models, kind of a spaghetti, whatever you want to call this damn thing? I don't think I can.
This is a foresight project from the UK. Yeah.
So to push back a little bit on what you were saying, I mean, I think it's a fair analogy, right, is between Newtonian physics and quantum mechanics. You don't need quantum mechanics to build a chair, right?
Yeah, that's right. That's right. There are some spheres.
Most of the things we do as humans, we don't need anything but Newtonian physics, right? Unless you want to go to whatever.
Right.
Off the ground.
Yeah, I mean, I think there are certain spheres where
You made it even more complex.
you don't need it. But, again, I'm surprised. So we're working with Neil Helfand's group, for example, out of UCLA on issues having to do with dental care. I always thought dental care was a pretty straightforward issue. But when I've really been talking with them about it, I realized, okay, the profound issues having to do with, where a complex systems lens is not only desirable, but arguably essential to get meaningful policy advice out of it. And they do have to do with trust issues and language barriers, but also issues having to do with the interaction between care seeking on the one hand and individual protective behaviors and risk behaviors. The fact that care seeking provides a way of not only drill and fill, but also a way of counseling a patient, how to change their behavior, and an individual who presents for care may therefore, have both protection as a result biomedically of the appointment, but also protection in terms of some measure of change in their behavior. And that's an eye-opener. I think it'll be a long time between, really what we're dealing with here, folks, is that the training involved, the number of people out there who do this sort of systems modeling for health is very limited. It's very limited. And if any of you are really, really interested in this, there's a bright career ahead. There's huge demand for this stuff and too few people. Why do you think I'm flying to Sydney, right after this?
Next going to Australia every other month, really, so my hope for this so-called boot camp people.
Yeah.
So my hope is to bring Nate here at boot camp for 4 or 5 days. That's what we need, hopefully in Colorado, so that
it'll be a real honor. But genuinely, I think, 50 years from now, I suspect that a lot of problems that are viewed as realistically purely biomedical will have some interest in complex systems lens applied to them. But I do think there'll be certain ones that are still comfortably dealt with traditional techniques that are really good fits, and there will be a long time before the priorities are such that we have the luxury of of approaching bone setting with a system science lens. So a couple more points, and then we'll break here after this slide. So models here express dynamic hypotheses about processes in the world underlying observed behavior. So they're not models of externally observed behavior. They're models sort of how we posit things might be working out there in the world in ways that might be explanatory for understanding observed behavior, but fundamentally it's about making, drawing consistent, reliable conclusions from our understanding of how the world might be working, and more quickly being able to make sense of the latest evidence in terms of whether it jives with how we might think it works. If it's all trapped in our heads, we are just terrible as people, and there's all sorts of experimental evidence to suggest this. Even they've done these studies with MIT graduate students in science, technology, engineering, and math, and they've extremely simple mathematical formulations, which they understand very well, the differential equations behind them, and asked them for the implications of them. They're terrible. They're terrible about reasoning it through in their heads. We're just not set up to do that. My colleague Jeff McDonald of University of New South Wales taught models as learning processes, in the sense that a crutch helps us deal with a limitation of ours. Models help us deal with this limitation of our noggin in terms of adding things up to make sense of it. Models help us understand how diverse factors related to health disparities combine to yield observed patterns, and how intervention might affect health disparities. They're specific to purpose, like math, remember, and like maps, they are wrong, they are complete, but they help us behave more reliably and usefully in the world. And multiple and hybrid modeling types we'll be getting to next are complementary in characterizing complex health. Okay, so I'm sorry for taking so long before the break, but I think we can have a break for a little bit.